Good morning. I'm Raymond Seidel. I'm the scientific director of Schloss Dagstuhl. For those who don't know what Dagstuhl is, it's the computer science version of Oberwolfach. For those who don't know what either of those two is, just ask people around you. I have the honor to lead through the first session this morning and to start out with a question to the young researchers here. Who is interested in advice on having a bad career? If so, David Patterson, our first speaker today, is a perfect source for advice, along with lots of good advice to have a good career. Actually, he's a source for good advice for all kinds of things, like how to run a big research project. And all those pieces of advice are kind of reduced to the essential, to the important. So coming to the reduced, he also reduced the instruction sets of processors to the important and the efficient. Among many other things he has done, like for instance, he was one of the co-inventors of RAID, so redundant arrays of independent disks, something that many of us maybe even use at home today. And I'm very happy that he'll tell us a little more about reduced or computer processors and what they're going to be this morning. So please, Dave, have the stage.
He might not agree with me. A very, very long word.
Okay, I am going to attempt to give a talk where I will explain the jargon as we go. Which, not a lot of math, but we've got a lot of jargon in our talks. But I would need the slide that's on the projector to be projected. Do I need to? I don't think I have to do anything. It should be on one of those two screens. But I could tell you while we're waiting for the screen to come up, we are doing something at Berkeley right now to celebrate our record in Turing Awards. Remarkably, there have been 7 research projects at Berkeley that have led to Turing Awards, and so we're starting a series. In fact, it started in the middle of last night with Shafi Goldwasser doing it. To the people in the back, I'm up. Okay. So this series is going to be every Wednesday. It's 1 o'clock in the morning German time, but 4 o'clock on the West Coast. And you can see several of the people here are going to be speaking. Shafi gave the first talk last night to an overflow audience that's in the back and then in the room outside. So I think this will be well attended. And it's broadcast as well as videotaped, so you can follow along this record. So what I'm going to do today is give you the history of computer architecture, 50 years, half a century in 10 minutes, and then talk about some of the challenges and opportunities, but it's a subset of the talk for the Turing lecture that's already been presented, you can see there. So, and I think from that half century, there's 3 lessons that will drive the future as well as it drove the past, is that software advances inspire hardware people, that when we raise the hardware-software interface, that leads to great opportunities in architecture. And finally, the way we settle debates in computer architecture is we spend billions of dollars building products, and then the winner won, I guess. So let's go back more than 50 years, and IBM had this problem. They had 4 independent lines of computers. And principally, they had different instruction sets. So what's an instruction set? So when the hardware is directed by software, it has a vocabulary. And that vocabulary is what we call an instruction set. So they had 4 independent vocabularies, so they had 4 different software stacks, 4 different market niches, marketing teams on it. So IBM engineers decided that was a bad idea, so they wanted one vocabulary for all markets, one instruction set to rule them all, so that was the IBM 360. Now the problem with those 4 independent lines of computers, and to get them to do the same thing, they needed some kind of gimmick, some kind of idea why they could do it. So they went back to one of the pioneers of computing, Maurice Wilkes, who was the second person to win the Turing Award, and he had an idea that was inspired by software. So then and now, the hard part of computer design isn't the data path. That's kind of the brawn. That's the thing that does the work. It's the brain. It's the control that's the hard part. So his idea is that we could specify the contents of the brain as a two-dimensional array, where every row of that two-dimensional array is, he called that a micro instruction, and you put zeros and ones to control it, and then the process of filling in that array was called microprogramming. And the technology to build that is typically a read-only memory, that its contents is filled at manufacturer, and that was much cheaper than doing it in logic. So that was the first example of software inspiring hardware. So IBM took that idea and in April 1964 made the biggest announcement in the life of the company. They announced this new idea of a family of computers that all could run the same vocabulary, the same instruction set, the IBM System 360. Here's 4 examples. You can see the data path, the thing that does the work, varied from 8 bits to 64 bits, so that's a factor of 8. And the speed varied, and the cost varied a lot. So the 8-bit one was $1.5 million in today's things, and the big one was $8 million. So IBM bet the company on this idea, and they won the bet. This led, who led this? The person in the front row. That's Fred Brooks a couple of years ago. And, but he got the, he's another Turing laureate, and part of the reason he did it was for the System 360, one of the most famous computers of all time. This is where if you want to know why a byte has 8 bits, it started with this computer. No computer before that had it, approximately, and all computers since then have used the 8-bit computer. So that's microprogramming. Now, Moore's law is coming along, and we're using integrated circuits. And before, where the read-only memory was a lot cheaper and faster, now they're built all out of the same transistors, so everything's about the same. And instead of read-only memory, it was about the same cost as memory that you could alter, called RAM. But with Moore's law, this idea that every year you'd have twice as many transistors, the memories were a lot bigger. So this meant that the vocabulary, the instruction set, could be much richer, a much bigger vocabulary, because the control memory was bigger. And a classic example of this was the digital equipment's VAX, a so-called mini computer, where the 360 was a bigger computer, a mainframe, and it had a lot of microcode in it. Next comes the microprocessor revolution. So instead of lots of chips, we could do a processor in a single chip. But now the people who did this, companies like Intel, didn't know a lot of computer architecture. They were chip designers, so they just pretty much followed what the big computers did. And what they would do is compete against each other and add instructions to the vocabulary. And the way they would say it was a good one is, look, here's an example. We write in this very low level, showing you an example of how to do that. It was pretty easy because of the microcode to add these things, so they were battling minutiae here. Gordon Moore of Moore's Law was a visionary. He thought back then, when they had an 8-bit microprocessor, that the next instruction set, the next vocabulary they did, Intel would be stuck with it for the life of the company. So he hired a bunch of PhDs in computer science, sent them up to Portland, Oregon from California to invent the next great instruction set. And it was certainly the most ambitious project of the 1980s, and it would be, or 1970s, and it would even be ambitious today. They had what was called, instead of 8-bit computers, it was 32-bit, and they had an idea called capability-based addressing, which was more secure. And they even wrote their own operating system in Ada, which was a new language at the time. So it was ambitious, but sadly it was late. And had lots of performance problems. It was several years late. So they had to go tell Gordon Moore, I'm sorry, you sent us to Oregon to invent the next instruction set. We won't be ready for several years. So Intel was forced to start an emergency project to provide the 16-bit microprocessor that the market was going to need. So they had 52 weeks to do the project, and everything, instruction sets, vocabularies, and building chips. So they spent 3 whole weeks on the instruction set, 3 weeks. And with 3 people, so it was about 10 weeks on the instruction set. So they basically just extended the old 8-bit microprocessor instruction set to 16 bits. And then they went off and built it. And it was announced to not much fanfare. To Intel's great fortune, IBM had decided to compete with Apple with the personal computer, and they needed a microprocessor. There was another one, the Motorola 68000, that was much like Fred Brooks's instruction set, more elegant, but they were late. They didn't have time for that, so they went with the 86. So the sales at the time when IBM did it thought they'd be 250,000, which is pretty good, but they were wrong. They were dead wrong. It was 100 million. So overnight, the emergency replacement 886 became a huge success, and because software that ran the PC would run on the 86, it suddenly became the future, and so Gordon Moore was right. It is the instruction set that Intel's been stuck with ever since, but it's just the emergency replacement one, not the one that the Oregon people were supposed to do. All right, now we start looking at these microcoded instruction sets. So you can think of them, what computer people think of it as what's inside is called an interpreter, and it comes from language translation, right? If somebody is giving a speech through an interpreter, it's kind of slow. So the one way you could do it is through interpretation, but the other way, you could translate the speech in advance, and you could read the speech much faster. So the question is, how good are these microcode interpreters? This is a picture of John Koch, another Turing laureate and one of the pioneers in both computing and compilers. By this time, and so in the 1980s, we've gone away from programming and assembly language at the very lowest level to high-level languages. The Unix operating system demonstrated you could even write an operating system in a high-level language. So now what we cared about was the output of these translators, or what we call them compilers, not what somebody would program in the low-level details. So John Koch built a kind of a mini computer at the time that had some of these ideas about a simplified instruction set, but maybe even more importantly, he had made advances in compilers. So he asked this question, or his group asked this question: suppose we take this compiler technology for the IBM 360 instruction set and only use the simple instructions, don't use the complicated ones. What would happen? Well, it ran up to 3 times faster by leaving things out. So that's a disturbing result. And over at Digital Equipment, where they had the VAX, engineers measured that computer and to their surprise found that on average it took 10 micro-instructions to get work done. When people thought it was 4 or 5, but it was actually 10. But then in terms of the instructions themselves, this vocabulary, 20% of the instructions were 60% of the microcode, and they were almost never used. So why is this here? So this leads to transition in these vocabularies from the so-called complex instructions to reduced instructions, or a simpler instruction set. So we have these alterable memories that used to have these microcode interpreters, and the big change is to go what's called a cache. So cache is simply a small, fast memory that has recent instructions, and it turns out the way we write programs, if you've used instructions recently, you're likely to use them again. So that's a cache. So now it just doesn't have an interpreter, it has whatever it's running on the computer. So that's, again, one of these software concepts about compiling or translating versus interpreting. And the instruction set was really simple. It's about as simple as the micro instructions that Maurice Wilkes talked about. They're just not as wide. There's this idea of pipelining that it enables, which is a computer architecture go-to idea. It's kind of like manufacturing a car where you do one step at a time and you can do them in parallel. And by the way, the complicated instructions weren't used all that much anyways. And then finally, there was a breakthrough in compiler technology based on making the analogy between graph coloring and what's called register allocation. So registers are kind of the bricks of computer architecture. They're the fastest memory that we have. There's not very many of them, and so you have to use them efficiently, and this compiler breakthrough based on the graph coloring algorithm made them run much more effectively. So that led to this transition to RISC. How do we explain why a simpler instruction set was going to work better than a complicated instruction set? If you think about, vocabularies, you could think of the complex one as having lots of $5 words, so it shouldn't take as many of those to complete a program. You should kind of read or execute fewer of those, and that's the number of instructions per program. So what happened was, that's true, but how many fewer? So it was typically about 25% fewer of the complicated instructions. But then the question is, if you're reading this vocabulary, how much faster could you read it? Well, it turned out for the RISC designs, they could read it maybe 5 or 6 times faster, so the net effect was about a factor of 4 advantage. So this formula, which we didn't have and kind of knew intuitively, but it wasn't really spelled out, was actually first appeared in a book like this. I'm surprised I can't find it earlier. And so this book attempted to make computer architecture more quantitative. And in fact, the endnotes tried to be like a physics textbook that had lots of formulas that you could use to design computers. So this is when Berkeley and Stanford kind of enter the scene. The first microprocessor using the RISC ideas was called RISC-V. That happened in 1982, and then in 1983-84, there was a second design, and also done at the same time at Stanford. These last two were presented at the leading computer circuits conferences held in once a year that thousands of people attend. And I can still remember being there in the audience when the Berkeley and Stanford presentations were done, and there was a murmur after the presentations, and it was a remarkable moment in time when a handful of grad students at Berkeley or Stanford could build a microprocessor that was arguably better than what industry could build. So what's bringing up today, wrapping up our 50 years of history, Intel didn't take this lying down. They had this complex instruction set that was compatible with all PC software, so it was very valuable. So what they did, remarkably enough, is I told you about the translation that would typically be done in software. They did it in hardware. They put a front end on their hardware that while the program was running would translate it from the complex instructions to basically the RISC instructions, and then thereafter anything that the RISC people did, they could do. So with more engineers and better technology, they basically took over the marketplace, and at the peak was 350 million chips a year, and they dominated both the desktop and the servers. So that's the PC era. We are in the post-PC era where things are in the cloud or in your pocket. That's a big change. Instead of buying chips from a company like Intel, you have designs called intellectual property that goes into a system on a chip that you're building, like would go into your phone. And now it's not just performance, but it's die area and energy. So this extra overhead that x86 has to do this translation on the fly is expensive. Remarkably, last year, there were 20 billion chips that had microprocessors in them, and 99% of those are RISC. So again, the marketplace settled these debates. The PC era went to the CISC, and this post-PC era is RISC. Okay, so that's 50 years. What's going on now? Moore's law is really over. So the reason, a remarkable projection. In 1965, he said doubling number of transistors, the building blocks of chips every year, and then he amended it in 1975 to doubling every 2 years. Using his slower projections, we're off by a factor of 15 using Intel technology. So the reason this is shocking is that people have claimed this many times in the last couple of decades. It's over to be wrong, but it's really over. So this is for those of us who've had 50 years of Moore law, this is a kind of a shocking event, but we're now in the post-Moore era. A lesser known, but maybe equally important observation was by Robert Dennard, that he said, well, how could you keep putting more transistors on the chip without the chip burning up? And his observation was the voltage would shrink, so the same area of silicon would remain the same power, and you could see, if it goes back to the 70s, it was very flat, that blue line, and suddenly it goes up. So now we're limited by power on the chip more than we are by the number of transistors. When you multiply those together, the first figure of that textbook that we talked about, there was the good old days when performance doubled every year and a half, and for those of you who are too young for this, we would throw away perfectly good computers because your friend's computer was 3 times as fast as yours and you wanted to be as fast. And so these days we keep laptops, I don't know, until they break, right? Because as far as we can tell, there's no difference. That's the result of the end of Dennard scaling, something called Amdahl's law, where because we switched to lots of these processors per chip, there's a law of diminishing returns. And in this last year, the performance improved only 3%. So that's double. So we went from doubling every 18 months to doubling every 20 years. So it looks pretty bad. So what advice do we have? So this is from Bertha Calloway. We cannot direct the wind, but we can't adjust the sails, okay? So this is a reality we have to live with. What are we going to do? And I'll talk about a couple of opportunities here. The software-centric approach, modern programming languages, not like what some of us learned, are amazing in terms of their productivity, but they're really slow. And I'll give you an example of that. So Python's probably the most popular programming language. I'll give you an example about how slow Python is. From the hardware-centric things, computer architects, the only thing left is what's called domain-specific architectures. We can't make single processors any faster. There's a limit to how many. When you put lots of processors on a chip, the only thing left is to do something specific, not general purpose. They do a few things really well, but they don't do everything. And you can combine these two together, which it gives another one of these lessons by using a domain-specific language that'll raise the level and allow us to innovate. So let's talk about Python. So this is an example of matrix multiply in Python and how much faster it can go. So if we rewrite it from Python to C, we can go 50 times faster. Now, because it's running on a multi-core computer, multiple processors, if we go in by hand and identify the parallelism, we can get another factor of 7. Now, these caches I talked about, these temporary fast buffers, those are very important for performance. So if we carefully lay things out so it uses those caches well, then we get another factor of 20. And then finally, there's something called single instruction multiple data, where it puts special purpose instructions that can do 16 32-bit operations every clock cycle. If we take advantage of that, we can get another factor of 9. Multiply those all together, and what's being left on the table? A factor of 63,000. As John Hennessy says about this, if you're dealing with C or C++ and you're a compiler person and you can make it go twice as fast, you're a hero, right? You're a hero to be able to do this. So there's opportunities, there's Turing Awards waiting to be picked up here. If you only make it go a factor of 1,000 faster, that would be an amazing result, but that seems like that potential is there. Now, domain-specific architectures. So you tailor to a somewhat narrow area, and it runs a set of applications. Some people are confused by the phrase application-specific integrated circuit. It doesn't run only one thing. It runs a domain well. There's still software running on it. Why does it run faster? So this is the one I'm going to have a hard time avoiding jargon, so forgive me. So basically there's two kinds of parallelism often done. One instruction at a time, lots of data. That's more efficient than when you're running lots of independent programs, so-called MIMD. And there's something called very long instruction words, where it's under compiler control versus modern computers do out of order. So basically the parallelism is easier to control and more efficient. Using those caches well, the caches are great. They're probabilistically guessing what you want, but under software control you can have better idea than with caches. And the last one, which is pretty easy to understand, is instead of using very wide precision that you need often in general purpose computing, in domains you can get away with narrower data, which makes it run faster. The problem has always been for special purpose architectures is where are you going to get the software? But because of the domain-specific programming languages, which are attractive to make the programmer more productive, they raise the level of abstraction, which allows us to map that onto special purpose hardware. So who are we going to help? Here's a field where the number of papers grows by Moore's law. And that field, not surprisingly, is machine learning, deep learning. So plotting this, it's doubling every year. If you want to keep up, as of the end of last year, you need to read 50 papers a day on archive. Okay, 50 papers a day. So this is a pretty exciting area. A lot of talking about it. What can we do to help it? So this is called the TP from Google. This is the Tensor Processing Unit. It was announced in May of 2016, so just 2.5 years ago. If you use Google, you're using it, right? It's been in production for 3 years. It's using queries. It was helped used to win the AlphaGo match. And it happens to be on the cover of this issue of the Communications ACM, the ACM flagship, if you want to learn more about it. Why is it so much, why are people excited about it? Amazingly enough, on this single microprocessor, it has 65,000 multiply accumulate units, 65,000. That's like a factor of 100 more than most processors today. Why can they do that? Because they throw away the general purpose stuff and they dedicate it to the application. It also has a lot of memory on the chip, which is important for both speed and energy efficiency. How much faster is it? It's 15 to 30 times faster, but a particularly interesting measure is the performance per watt because we're limited by power, and then it's a factor of 30 over GPUs and 80 over CPUs. Google measured this on production applications, but that's internal. How are we going to do this? And so there's recently an attempt to have a standard benchmark for machine learning so that everybody can measure them. And that's starting to happen. It's happening, I guess in a couple of months you'll see those results. So I talked about way back in May 2016, what's been going on in Google lately. They've announced 2 more generations. In May of 2017, they announced TPU v2. This is not just for inference like the first one, but it's for training. And not only is there that board, but you can put them together in racks, and the peak performance is 11 petaflops. The following year, they announced one that was liquid cooled so you could do more power, and it's a bigger multiprocessor, and it's more than 100 petaflops. So how much is petaflops? So there's something called the top 500 supercomputers using a different measure, but it's called petaflops, but they're bigger petaflops, and there's 32 and 16 bits. But ignoring that, 64-bit floating point. So the 16th fastest computer in the world is 11 petaflops, and the 4th fastest in the world is 100 petaflops. And Google's not building just one of each of these. They're building a lot of these. So these are going to be the kind of supercomputers for machine learning that you can program in Python and TensorFlow and PyTorch and things like that. Okay, so what's happening right now? It's a very exciting time to be a computer architect. There are these big debates going on with companies placing different bets with different architecture schools, and we'll see what's going to happen. Google tends to do these big multiply units. NVIDIA has lots of cores, and they do what they say, lots of threads. Microsoft is using these flexible hardware devices. They're betting on that, and Intel's betting on everything. Intel's bought companies, so they have some of those and some of these and their own designs. And amazingly enough, there's at least 45 companies, startup companies, doing machine learning hardware. And so what's going to happen? I don't know who's going to win, but I can tell you who's going to determine it. It's going to be the marketplace. We're going to spend billions of dollars, put these things out there, and people are going to decide which one's the most effective. Okay, and then I'll go through one more opportunity here that's again inspired by software. So open source. Why is there open source hardware, open source software, but no open source architectures? This takes us to RISC-V. This was the 5th Berkeley instruction set. RISC instruction set. It was time for us to do something. The proprietary ones from these big companies, Intel and ARM, they were not only really complicated, so unattractive, but it was illegal for us to use them. They wouldn't let us use them, so we started building our own. It took us several years. It was led by my colleague Krista Sanovich and 2 star graduate students who did this work. It took us 4 years to do it. We had built some chips along the way, but then we had this funny thing happen. Companies were complaining about us changing our instruction set, our vocabulary, inside our courses. Why are you complaining about us changing our instruction set for our courses? And what we realized in talking to them, there was this thirst for an open instruction set. They looked all over the world. They liked ours, started using it. Once we heard about that, we thought that would be great and wanted to make it happen. So why do they like it? It's a real simple instruction set. It's a very simple vocabulary. We're 25 years later, so we could avoid the mistakes of what had happened in the past. It allows it to be expanded. It supports these domain-specific architectures, but the biggest difference is it's run by a foundation. So it's not owned by a company, but by an open foundation. So this foundation, it started 3 years ago, and now there's, I think, over 200 members, including big companies that are promising to ship it with their products. Interestingly, the way its design's being done, it's something like a standards committee where when a topic comes up, we bring experts from all over the world to talk about it, and then they reach consensus before it's embraced, where typically for proprietary instruction sets, the companies announce it, and then everybody tells them what's wrong with it, so we do it in the other order. It's not just RISC-V, there's also NVIDIA has an open instruction set. It's one of these domain-specific architectures where everything is open, the software, the hardware, the implementation. So this is a new thing. So I purposely kept this talk short so there's time for questions. So the lessons of the last 50 years, software can inspire architecture innovations. That was this microprogramming idea from the IBM 360 days, RISC ideas about this translation versus interpretation, and open architectures. Raising the interface enabled going to high-level language labeled the RISC ideas, and now looks like it's enabling these domain-specific architectures. And then the marketplace, sadly, is how we settle these things. It's not fair, but that's the way it does. And right now, IBM was a big winner, and the Intel architecture in the PC era and RISC in the post-PC era. Open versus proprietary instruction sets, which domain-specific architecture is going to win? Who knows? We'll find out in a few years. But it's a really exciting time in computer architecture, and we think it's going to be another golden age. And with that, I'm open to questions. And at the end of the questions, I'm going to try something. So I see a hand up. I see hands up. Assuming microphones are on their way. Yeah, microphone is on its way.
Thank you for a nice historical talk. What I was wondering about is what do you think is the role of academia versus industry, given that this is such a market-driven area?
Yeah, so I think one of the things I really like about computer science is we have a synergistic relationship with energy. I think some fields it's antagonistic, but we have, I think we think of our academics, think of them as our industrial colleagues, it's our former students at these companies, and we're all trying to make, better computing technology. It's the companies that embrace these ideas, but certainly my career was in academia, and I felt I had plenty of opportunities to influence what was going on. I don't see any reason you can't change the world from academia continually. So companies turn these into products. We don't turn into products, but we can influence things. What's particularly exciting right now is with RISC-V, and so there's an open architecture. Before you'd have to convince ARM or Intel to use your ideas. Now you can demonstrate your ideas in RISC-V immediately, and other people can embrace it. So I think it's even easier now, which is another reason why I think it's a golden age. But it's a great time either in academia or in industry for architects. Other questions?
Thank you so much. I want to find out, I saw when you wrote something on GPU, NVIDIA GPU. And when you're working with artificial intelligence techniques, something like deep learning and neural nets, you mentioned it there too, they tell us that it's computational intensive. And everything we talk about
is expensive, is that what you said?
Yeah, computational intensive, which means it takes a lot of the resources. And that's the memory, the GPU, the RAM. Now, I want to know what is it that makes it so difficult for people to use it. They always need a system that has GPU.
Okay.
And such systems are usually expensive. So what is it about this resource that is so expensive?
Yeah, great question. So you can do all your work on a standard computer. You can do it all. You can just use a standard laptop. If you want to go fast, you got to do something else. So to NVIDIA's good fortune, they built a chip that was special purpose for graphics, which accelerated single precision 32-bit floating point performance. And that's why they're building it. Turns out, for machine learning, 32-bit floating point is plenty enough. So they had a market-driven force to build a chip that costs hundreds of dollars with very high single precision floating point performance. So Jeff Hinton and his students in 2012 when they were doing machine learning, used a GPU that was intended for graphics to do machine learning. So it's a lucky combination of an inexpensive, I think hard to use, but inexpensive high-performance chip that they're mapping software to it. So conventional wisdom today is that is the best hardware for doing machine learning. But many architects think there are better ways to do it. So Google, Microsoft, Intel, and 45 startup companies think there are better ways to do it. Who's right? You know, the marketplace will help figure it out, but it's part of the excitement here. Okay, I think I'm, okay, one more and then I'm going to try this experiment here.
So what do you think about many core chips, chips with, say, thousands of cores? This is a way to overcome some obstacle of the Moore's law, you know, this.
Right.
And my feeling is that this technological solution did not deliver what we expected because we could not effectively use all the computer power offered by many core platforms. What do you think about that?
Yeah, I think that's a fair, you know, out of necessity we went to multi-core just because we couldn't make faster single core, and it was hard for software to take advantage of it. The comment though is because now that the future is domain specific, ideas that wouldn't work for general purpose computing might work well in narrower areas. So certainly all the old ideas in computer architecture or in computer design are being reevaluated right now on domain-specific architectures, particularly for machine learning. So Ivan Sutherland loves asynchronous design. There's asynchronous companies. There's people who are doing multi-core designs. There's field programmable gate arrays. Kind of all possible ideas are being reevaluated given this opportunity in domain-specific architectures. So it's hard to say something won't work because it didn't work in the past, and it may work now. And you know, it's an exciting, interesting time. Okay, so I'm going to try this idea that for the YRs, I guess, is some people think that because if you've had some success, your road has been perfectly smooth right to here. You just woke up with a silver spoon in your mouth and as a baby, and life has been beautiful all the way. So I thought I wanted to tell you how I got here, but I need the slides. So I'm an accidental Berkeley professor. So how's that? I seem to have a delay here. Okay, so what happened? So I'm the first of my family to graduate from college. My dad went to college, but he didn't finish before I did. But I had no plans for graduate school or no plans for computer science. There was no computer science major. I was a wrestler in high school and college. So what happened was I was a math major, and then in the end of my junior year, a math class was canceled. I had to find something in that time slot, and it happened to be a computer science class, an intro class. It was only a half of a class even. But despite how primitive it was, I was hooked. So my senior year, I took as many classes as I could in business and in engineering, and kind of did my own informal degree. So in my senior year, the middle of my senior year, I took a class from a person, and I was working in my dad's factory to support us going to college. And I said casually at the end of the class, boy, I'd sure rather do computing stuff than work in a factory to go to school. And on his own, he went and found me a job as an undergraduate. And so I started working with grad students. And back then, I could apply for grad school. I talked to my wife and said, what about a master's degree? Seems pretty cost effective. It'd only take 4 quarters and I get a master's degree. She said, sure, why don't you do that? And then I was put in an office. There was 4 of us in the office. The other 3 people were all getting PhDs, so that seemed like a good idea. So I talked to my wife and she said, well, if you think you can do it, go for it. We had 2 sons, and then we're living on a 20-hour-a-week research assistantship, so we're pretty poor, and then the RA ship ran out, which was bad, but my advisor helped get me a job at an aerospace company building airborne computers, and it took me another 3 years or so to get my PhD. Now my wife was from Northern California, I was from Southern California, and she always wanted to move back to Northern California. So while I was a graduate student, I was starting to get job offers, but I hadn't heard from Berkeley. So she forced me, as a grad student to call the chair of the department of UC Berkeley to find out what happened to my application. And I can still remember the dread of getting on the phone and talking to Ellen Burleykamp, who's a famous mumbler, and trying to, I hadn't heard from Berkeley, that's one place that I would consider if I'd heard from. And so he told me, well, Dave, you're in the top 10, but not the top 5. And I remember this tremendous sense of relief that wasn't as bad as I thought, hung up. So it turns out I found out later, he said that to anybody who called. Top 10, that's fine. But he took my application, gave it to a person who was visiting Southern California. We hit it off. I got an interview and got a job there. And then the first project that I did with that professor was way too ambitious. We didn't have the resources. We were going to build operating systems and build chips and stuff. But kind of remarkably, I took a leave of absence from Berkeley and went to Boston and I used that time to rethink my career and came back and did the RISC stuff. But even tenure wasn't easy because computer science is strange in that it values conference papers instead of journal papers, and everybody else follows journal papers. So I think my case was difficult to make, but it was that they made it, and since then things were better. So it's not a smooth road all the way. I started. If they don't stop me, I'm going to do. So I was going to say what worked for me. So what worked well for me? So, in America, you think wealth is equal to happiness. It's not. There's a lot of unhappy, wealthy people. I think one of them is our president right now. So I just maximize happiness directly and not always for wealth. Family first, I had some time to think about it, and in a busy job like this, if you don't make the family first, the family can end up pretty far down the list. Passion and courage. I like to think I'm a logical person, but I'm really a very passionate person. And then ironically, the physical courage that came from wrestling has translated into intellectual courage, and I feel it's my individual job to stand up if something's not right and try and stop it. So the passion means, in using baseball terms, but may not work here, is we swing for the fences. We try and hit home runs rather than play it safely. That's when I was a new professor, they say we value positive impact, not paper. So I believe in that, and so that's what we tried to do. Now one of my colleagues told me, this was Lathi Zada, and I think he told this to me because I'm a passionate guy and would confront people, but he said, friends may come and go, but enemies accumulate. So let me pass that on. Your friends, kind of fall apart, you don't see anymore, oh yeah, we used to be friends. Enemies never forget, okay? They're always your enemy. As far as I know of 2 enemies I made, and it was big, difficult. One was a big, difficult decision about hiring a person, and that person was an active enemy for the rest of my career. But the other person I picked was the head of DARPA under the Bush administration, because I thought he was doing things that were bad for our country and bad for our field, so I took him on. That was not a popular idea because he was a vengeful person, but so many people hated the guy, it turned out to be a good career move. But it didn't seem like it at the time. Winning as a team versus an individual. I'm a wrestler, which is an individual sport, but my coaches said if we bond as a team, we'll be more successful. So I just believe this in my DNA. And quoting Fred Brooks again, quoting Fred Brooks, who quoting the basketball coach at his university, there's no losers on a winning team and no winners on a losing team. So if you win, everybody wins. If you lose, everybody loses. And I just believe that in my DNA. I think I'm good at getting honest feedback and learning from it. It's easy to avoid feedback. It's easy to get, but when somebody doesn't like what I'm doing, I give them my papers because they'll tell you what they think for sure, and you need to learn from that. The warning sign that I would pass along, if somebody thinks they're the smartest person in the room, run away. So the examples are the president of Harvard thought he was the smartest one in the room, and he was fired. The founders of Enron are both convicted felons, and I actually have a relative of a brother-in-law who thought he was the smartest person in the room, and he's in prison. So why would this be? I think it's because if you think you're the smartest person in the room, you think, what could I get from any of you? I'm smarter than all of you. Why do I want your feedback? And if you don't get feedback on your ideas, bad things can happen. But in any case, if you learn from somebody who thinks they're the smartest person in the room, don't do anything that they do. And then I still remember kind of waking up, in the morning, and it was like God spoke to me in the sunny day, and he said, It's not how many things you start, it's how many things you finish. And it was like, I was thunderstruck. And since that moment, I tried to do only one thing at a time. So when Hennessy and I did our textbook, that was the one big thing I did. When I was president of ACM, that was one big thing I did. But if you only do one big thing, say a year, over 40 years, you can get a lot of things done. And a lot of academics just say yes to everything, and it's hard to finish that. And then finally, I'm a natural-born optimist. I think optimism is a better policy. You know, if you're trying to run to get a bus, if you don't try to run, you're not going to catch the bus. You have to be cautious but optimistic. And my story goes back to when I was 16 years old, to illustrate what an optimist I am, is I started dating a girl, and she had dated lots of other people and wasn't interested in being exclusive, or what we would said then going steady, but I screwed up my courage and asked, could we go steady? And so she said to me, because she felt pity, I don't know how to say no. Well, as a logical person and an optimist, not a no was a yes, so I said, great! And so she didn't know what to do, but figured she'd let me down. But we've been married 51 years now and hasn't let me go yet. All right, thank you.